up, man. I'm ready to go home. A lot of vocabulary, a lot of recognition and classification stuff in tonight's lecture, as it is. For the rest of the class, we're going to look at one point of view of differential equation solutions, and that is the analytical point of view. This is what you're more used to. When you took math courses throughout your history of mathematics, all you did for the whole time you were in the class most of the time was learn a method for doing something. Okay? So all that I'm going to do for the rest of this semester is learn a method of solution for a differential equation. We're probably not going to ever trace another direction field or do another numerical analysis project to try to figure out the solution. But we have to talk about those possibilities in this class. The rest of the time we're just going to spend learning ways to solve them outright and applying them to different situations. So this is the first thing, forms of differential equations. I told you last week, a differential equation itself is just an equation that contains a derivative. It contains a derivative. It can be written in lots of different ways. Derivative form means we're going to use the y prime or y double prime, y triple prime notation. That's derivative form. Differential form, you're familiar with that with calculus, dy over dx. That's the first derivative. Remember, for the second derivative, they write it this weird way, d2y over dx 2. That's not actually squared. That's just the notation for the second derivative. Look that up in any calculus book, that's the way that they'll put the differential form of it. I haven't ever seen it done this way, this differential operator form. I've never seen that. But when I was taking the notes for this class, this was a way that it could have been given. They said this was a possibility. I've really never seen this. You guys are going to deal more with these two forms in this class. You can have two types of differential equation. You can have an ordinary or a partial. Ordinary differential equation or a partial differential equation. Differential equations are classified as either ordinary, which they use the abbreviation ODEs. That's what you're going to do in this entire class. We're only going to study ordinary. We're not going to do partial. If you guys are taking a lot of math classes, getting your degree in either mathematics, possibly teaching mathematics, there's a class offered called partial differential equations. Totally different than what we're doing in here. I don't know that engineers would need it for anything. But a partial differential equation has a partial derivative in it. And y'all are used to seeing those like you've seen in Cal 3. They differ in the number of independent variables that the equation has. Ordinary DEs contain derivatives terms of one or more dependent variables with respect to only one independent variable. X would be your independent. Y, of course, is always your dependent variable. Most of the time your equations are y equals whatever. Okay? So y depends on whatever x is. This is an example of an ordinary differential equation. All your derivatives are of y. Same way here. This is an ordinary differential equation. In partial differential equations, first of all, the d's look weird. Y'all remember the funny looking d that they used? Okay? That's one thing. That's the dead giveaway that it's a partial DE. Okay? That you got that weird, funky looking d there. That's the second partial derivative of u with respect to x. So u is a function in x and y that way. So this is the partial derivative of u, second partial derivative of u with respect to y. So you got lots of embedded variables there. That's a partial DE. We're going to spend all of our time on ordinary. Types of ordinary differential equations. There are two types, a linear or a nonlinear. We're going to spend a lot of time doing linear DEs. Linear or ordinary differential equations of the form. Notice you can have anything in front of these y's, but notice your variables, for your y variable there, and your derivatives are all of the form where y is what's being primed. Derivative with respect to y there. An ordinary differential equation is linear if and only if all the coefficients are constants, which would just be numbers, right? Or functions of x. For example, the coefficient of this y could be cosine x. The coefficient of it. This a sub 0 could be x to the fourth. That's okay. This a1 here could be x squared plus 5 in parentheses. That still makes it linear. When you have a nonlinear, what happens is all the y primes and the y's and the y primes are not raised to a power. If you had y squared, it's nonlinear. Y to the fourth power, nonlinear. Y prime of x to the third power. If your derivatives are raised to a power other than 1, it's nonlinear. Okay? So here's an example of a linear equation. Look at these coefficients on your y's and your y primes. X to the fourth, that's a function of x. That's okay. X cubed plus 1 is the coefficient of that y prime. That's okay because it's a function of x. Tangent of x, that's the coefficient of that y. That's okay because it's a function of x. All this stuff is just x's. This is a linear, ordinary differential equation. Here's an example of nonlinear. Look down here. Look through that and tell me what problem there is. What's the problem with it? What causes it to be a nonlinear? What? Y to the fourth. Y to the fourth makes it a nonlinear. I'm going to give you one of those on the test, and I'm going to say, is this linear or non-linear? Okay? Is it linear? Sometimes it's hard. Sometimes you have to do a little bit of work with it, try to figure out. You may have to multiply things out and have it all on the list before you can compare the terms and see if it's linear or non-linear. If it was just y, there's your just y right there. Look through it, or you might be combined terms or something. Be careful. You should have a y. You should have a y. If you have a y double prime, you maybe have a y prime. Maybe have a y to the first, but you shouldn't go any other power higher than y to the first. Everything else should be functions of x. There's a couple. I think there's one in the homework that's really questionable. We'll go over that if you have problems with it, though. Order. You're going to be asked to tell me what order of a differential equation it is. Is it a first order, second order, third order? That's so easy. The order of a differential equation is given by the highest order of derivative that is represented. So is it a first, what does it have in it? Does it have a first derivative in it? Does it have a second derivative? A third derivative? In your first one right here, this is first order because dy over dx means the first derivative. That's why it's first order. Why is this second order? Why is this a second order? Y double prime. Remember that? It's the second derivative. That's second order then. This is a second order. Why is that a second order differential equation? Okay, but this will confuse some people because they don't get the definition that's right. It's the second derivative right there, so that's second order. Look at this. This is dy over dx. What's the deal with this? Is that fourth derivative? That is the first derivative that's been raised to the fourth power. So is this linear or non-linear? Non. Why is this non-linear? Derivative has been raised to a power. You can't have derivative raised to a power other than 1. Okay? Non-linear. What about that second one? Is that one linear or non-linear? Linear. Look at all your coefficients. Function of x, that's okay. Function of x, that's okay. Constant, that's okay. That's linear. That that second one, if you want to write that in there in your notes just as another example, that'd be great. The first two are linear examples, and the third one there is a nonlinear example. So, classification of a differential equation. If I give you one on the test, I can ask you, is it ordinary or partial? Is it linear or nonlinear? And what is its order? Okay, that's the three questions I can ask you as far as classification goes. Now, solving a differential equation. The solution to a DE is to find a function, y equals to something, which when substituted back into the original, satisfies that equation for all the values of x and y. So your goal in solving a differential equation is to get the derivative out of it. Get the derivative out. Find what the original function would have been. Determine whether y equals 1/2 e to the x minus 1/2 e to the minus x is the solution to this differential equation. The differential equation is y double prime minus y equals 0. Well, to see, we're going to have to see if the derivatives will plug into that equation and make it true. So we were given y. Let's find y prime. So let's see how good you guys are at taking derivatives. Got a big test on this next week, so this would be a good time to practice it. What would the derivative of 1/2 e to the x be? Good? The derivative of e to the x, remember, is just e to the x. The 1/2 constant is just going to stick around. Okay, look at the next term. Negative 1/2 e to the minus x. What's going to happen there? Okay, yeah, the derivative of e to the minus x is e to the minus x times negative 1. Remember, times that derivative of minus x would be minus 1. So it's going to change it to a positive 1/2 e to the minus x. Good. That's your first derivative. Question? That is the same thing as that, but you want to work the derivative. You want to do with work with the power. The derivative of e to the u is e to the u times the derivative of u. So for this verification, I need a second derivative. We're going to do it again. So y double prime. The derivative of 1/2 e to the x is? Okay, what about the second part? Okay, so to verify that, that's exactly right. So to verify it, let's see. Y double prime minus y should equal 0. Is that true? 1/2 e to the x minus 1/2 e to the minus x. That's y double prime. Minus y. What is y? The original. Good job. Is that equal to 0? When you subtract, what do you do with this minus sign? Distribute it. And sure enough, subtraction takes place. So you verify that that is a solution. This equation right here is a solution to this differential equation. It may not be the only solution, but it is a solution. Okay? It's a specific solution that would be the answer to a probably an initial value problem or something like that. Determine whether y of x equals c1 sine of 2x plus c2 cosine of 2x determine whether this is a solution to the DE, y double prime plus 4y equal to 0. So we want to verify that that's a solution. So here we've got y equal to c sub 1 sine of 2x plus c sub 2 cosine of 2x. So what would y prime be? Let's take it one part at a time. Get your calculus skills out here on this first one. What's the derivative of sine? Just cosine. So it's going to be cosine of 2x times the derivative of 2x, which is just 2. This constant is going to multiply out, right? Out front. So that would be 2 c1 cosine of 2x. Good job for that first term. What about your second term? The derivative of cosine is negative sine, so times 2 again. So this is going to be minus 2 c2 sine of 2x. You okay with that? The constant c2 is just going to multiply. So I need to do y double prime. Okay, so first term. Okay, the derivative of cosine is minus sine, so it's going to be the 2 times that 2 times c1. So minus 4c1 sine of 2x. Good job. Okay, and what about here? The sign doesn't change. Good, so minus 4c2 cosine of 2x. Good job. So now I can verify whether that works or not. So y double prime okay, plus 4 times y, which was your original, right? Equals 0, and I can tell that by looking at it. So I'm going to be a good little teacher and do all my work. Distribute my 4. Got news for you guys. If I make you do a verification on a test, I want to see your work. So 0 is equal to 0. It is a solution. It is the solution to that. Why can I say that other one a minute ago was a solution to that DE, and this one is the solution? Right? But, and this one I say is the solution, you don't know what C1 and C2 are, right? They could be any kind of constant, couldn't they? They could be constant, so those stand for any infinite set of different images that would work there as a solution. There's infinite solutions to that equation. But with the C1 and C2, it's a little bit less. That's kind of arbitrary. So that like takes care of all those solutions. The family of solutions. Okay. So here's a problem I want you guys to work together for what we just got through doing. Let's look at this. We're going to do several of these throughout the semester. So let's do this one. Verifying solutions. Exponential growth processes, for example, cell populations, bank accounts, involve functions of the form y of t equals c times e to the kt power, where c and k are greater than 0, can't be 0, and are real numbers. Where c is a real number and k has got to be greater than 0. Those are exponential growth processes. If k is less than 0, what kind of process is it? If your k was negative, what kind of process would that be? Decay. Good job. You either have growth or you have decay. Decomposition. So A part. Show by substitution that the function y of t equals c times e to the 2.5t is a solution of the differential equation y prime of t equal to 2.5 y of t, where c is an arbitrary constant. Then B part, show by substitution that the function y of t equals 3.2 e to 2.5t satisfies that initial value problem there. So y'all see what y'all can do with that. Help each other on it. Work together. Differential equations of a family of curves. Those c's that you've been seeing in the examples are called arbitrary constants. And they're often referred to in this class as parameters. Parameters on the differential equation. An nth order ordinary differential equation will yield an n-parameter family of solution. In other words, if I had a second order dE, how many constants am I going to have? 2. You will designate one as C1 and one as C2. Okay? If your dE has a third derivative, how many constants are you going to have? 3 constants. Okay? If you have a first derivative, how many constants are you going to have? 1 arbitrary constant. So I'm kind of going a little bit backwards here. I'm saying find a differential equation. Find a differential equation of this 2-parameter family of curves given by y equals c1 e to the 2x plus c2 e to the minus 2x. This is the solution set, guys. This is the solution to a dE. They want me to find the dE that this is the solution to. Okay? So let's try this. Let's take our first derivative. For me to have 2 constants, that means I've got to have at least 2 derivatives in this dE. So y prime would equal what? Nice job. Okay? Now what about a y double prime? All in favor? My signs all correct? Can I do any simplification on the right side there? Anything I could do algebraically to simplify that? Look at the expression in the parentheses. Y'all ever seen that before? What does that match? Your original equation, right? Your original solution. So can we say that this is all y? Can we say that? That something is y? So here's my differential equation. Y double prime equals 4y. Can I make that better? Most of the time you're going to see it as a set it equal to 0. So what do I need to do to get this equal to 0? That is a differential equation for that family of Notice since I had two specific arbitrary constants in there, my equation is going to have at least a second derivative. Okay? That one just worked out that way. They don't always work out that same in 3. I'm going to show you what you can do in the case where it doesn't. Okay? So, I love this. Find the differential equation of the family of circles centered at the origin. Pull some tricks out of your hat here from your algebra days. How do you write the equation of a circle centered at the origin? Equals what? If it was equal to 0, it would be a point. What would you have to make it a circle? Or a constant of some right. So you said r squared, that's fine. I'm just going to say sum. If I had any constant there, would it still be a circle? Y'all agree? So I'm not even going to put r squared. You're right, though. From an algebra perspective, that was the way we did the equation. But the radius is always going to be any constant. Even if it was 3, the radius would be the square root of 3. Okay? Any number there. So, how in the world do you take the derivative of a function like that? Or of an equation like that? Can we take the derivative of that? I would normally have to solve for y first, right? Solve it for y and then take the derivative. But we learned another way, if y'all can remember from Cal 1 days. Any ideas? Is it too late? Is our brain mush already? Did I kill y'all over in the computer lab? Implicit derivatives. Do y'all remember implicit differentiation? What's the derivative of x squared? What's the derivative of 2y? Good job. You had a great Cal 1 teacher, didn't you? 2y, y prime. If you take the derivative of a y, you put the y prime with it. Remember that? You remember those days? Equal to, what's the derivative of constant 1? 0. The derivative of a constant is 0. Good job. What do I need to do now? Solve for what? I'm trying to find a differential equation. I need to solve this equation for y prime. Good job. So I'm going to move the 2x over. Divide by 2y. What's that? Negative x over y? And notice that in my original equation, I had one parameter, one constant. In my DE, I've got the first derivative. That's it. All that you need. We did a direction field on that one last week. Y'all remember the one that had to look like a concentric circle? And it. Exactly the same problem we did. Look back at your notes to see the connection between those two things. That's the family of the differential equation for the family of curves centered at the origin. Let's do this one. Find the DE of the family of parabolas, y equals x plus c squared. How would that look? Y equals x plus c squared. Well, how do those graph out? You remember? It's x plus a number. What do you do when it's your curve, your upside, it's your U-shaped parabola in parentheses squared? How do we do that? Remember? It's be up or down if you had it outside of parentheses. This will be left and right. This will be all your parabolas. Shifted up and left and right on the x-axis. Okay? That's be all what you'll have right there. So, how in the world am I going to take the derivative of y equals x plus c squared? Anybody got to give that a shot? Chain rule derivative. So y prime would equal what? Two out front, right? X plus c to the what power? First times the derivative of the inside. What's the derivative of x plus c? Just 1. So you got y prime equal to 2x I don't like that. Right? The only bad thing is you can't have C in your answer. You cannot, if you're finding the differential equation, you can't have a C still left in it. Can't have it. How am I going to get rid of that C? Second derivative? I don't want a second derivative here. Why? I only have one constant. What would C equal here? How can I solve that for C? Got a problem right there. How can I solve that original equation for C? Okay, I'm going to solve this equation. Y equals x plus c squared for C. What do I need to do first? Square root. So the square root of y would equal x plus c. Everybody agree with that? Then what? Subtract x. Everybody agree with that? So let's see what we can do here. Now, y prime equals 2 times x plus radical y minus x. That's what C was. So if I clean this up, look, those things are going to drop out. So my differential equation is y prime equal to 2 square roots of y. Got rid of that C. So I'm making an early on substitution. And that's how you're going to do it most of the time right there. Find a DE for the family of curves given by so-and-so here. So I got 2 parameters, so how many derivatives do I got to have? At least a second derivative, second order differential equation for my answer. So let's start off taking the first derivative. Somebody hollered it out at me. Uh-oh. What happens in that second part? I change. Product rule. I'm going to multiply the constant times the product rule. Let's do the product rule. Is f prime g plus fg prime. So f prime, the derivative of x is just 1 times e to the 4x plus f times, what's the derivative of e to the 4x? So y'all are so smart. Some of y'all are so unsure to tell me anything. Here we go. Y prime equals 4c1 e to the 4x. Now I'm going to clean this up and distribute my c2. So this would be plus c2 e to the 4x plus c2, plus 4c2 x e to the 4x. Now, let's say, since you've got 2 c2s, let's get the c1 out of there. let's get C1 out of that problem. Let's go up here to the original and solve that baby for C1. I was first subtract that C2 x e to the 4x. For both sides. And then to get C1 by itself, what do I need to do? E to the 4x. So let's see what I can do here. 4 times C1, which we said was y minus C2 x e to the 4x over e to the 4x times e to the 4x plus C2 e to the 4x plus 4C2 x e to the 4x. A lot of algebra here. As you can see in that first term, look what happens. So that's going to give me 4y minus 4C2 x e to the 4x plus C2 e to the 4x plus 4C2 x e to the 4x. Anybody see anything else that I can fix? That's subtraction right there. So I've got, clean up one more time, y prime is equal to 4y plus C2 e to the 4x. Okay. So it's still not solved that you don't have the complete differential equation. First of all, I told you at the very beginning that you're going to have at least a second derivative of your equation. Well, we only got a first. And you've got that C2 still sticking out over there, so you want to get rid of that. Okay? So let's go to the next page and get some way. Y prime equals 4y plus C2 e to the 4x. Okay, so if I want a second derivative, I'm going to differentiate again across it. Okay, that's going to be y double prime equals, what's the derivative of 4y? 4y prime. Good job. Take the derivative of it. And then what's the derivative of C2 e to the 4x? Now, what I need to do is come up here, right here in this step, and solve that thing for C2. Solve that for C2. So y prime minus 4y equals C2 e to the 4x. So I'm going to divide by e to the 4x. That's going to help me make my substitution. So here we go. Y double prime equals 4y prime plus 4 times y prime minus 4y over e to the 4x times e to the 4x. Now watch how this cleans up. Those go away. And I'm not done. Y double prime equals 4y single prime plus 4y single prime minus 16y. So anybody care to tell me what my intelligent looking solution would be? Y double prime minus 8y prime, what? Equals no c's. You get all the c's out of the differential equation, okay? You have two arbitrary constants. You have a second derivative involved. Questions about that? Later on that'll be really, later on what I'll do is give you this, and you'll give me the solution. Right? I give you the solution, you have to do this. Later on in the class, I'll give you the equation, the big equation, you'll find the solution to it. Okay? Now, the total simplest method for solving a differential equation that there is. Can't always do it. It's very rare that you can do this, but when you can, you should take advantage of it. The simplest method for solving a CD is the straight integration. Straight integration. Back when I told you at the beginning, I said if I give you an equation that's got a derivative in it, to solve it, you're trying to get the derivative out of it. Well, what should pop into your brain automatically? What will undo a derivative? An integral. Okay? So that's what you're kind of doing here. dy over dx equals 4x squared. If I want to solve that, I can multiply the dx on both sides. Correct? And then integrate both sides. Integrate both sides of it. What is the antiderivative of dy? Y. What is the, and you're supposed to put plus c there, but since we're integrating, you can move the c's across the equal sign, so we'll just put c on one side only. Don't worry about putting it on both sides, you can put it on one side only. Okay? What's the antiderivative of 4x squared dx? Y'all remember your antiderivative plus c? And we can be technical here and say plus c sub 1. Okay? Since this is a solution, solutions can have the parameters in them, the arbitrary constants. The only way I can get c out is if I have an initial value or a boundary value that I can plug in. Okay? So, guess what that means we're doing next? To find the value of the arbitrary constant c, you must have a constraint on the original differential equation. This is called an IVP, or an initial value problem. An initial condition, y'all been doing this all night with that Euler's method mess. You had an initial value. An initial condition specifies point or points through which the solution curve must pass. So look at this one. Solve dy over dx equals 4x cubed, given that y of 1 equals 0. We already did the solution on the previous slide. So we know that y is equal to 4x cubed over 3 plus c. The fact that they gave us the initial value, we're going to plug in the 1 for the x and the 0 for the y. 1 for the x and 0 for the y. So 0 equals 4/3 times 1 cubed plus c. So that's 4/3 plus c. So what's c equal to? Negative 4/3. Good job. So tell me what the specific, unique solution is for this differential equation. That is the specific, unique solution, that solution curve that would go through the point 0, 1 that would have that differential equation. Questions on that? You know, you'd be up a creek if you don't know how to take the derivative of something and you don't know how to take the integral of something. Y'all agree with me? Those are some pretty handy tools to know. Y'all haven't even got into any really ugly, gross ones yet either. If you think about it. Nothing that's been too nasty so far. So just wait. Just wait a little while and you'll get it. An initial value problem, the x is always the same number. Initial value problems is always x is the same number. If you switch x coordinates, called a boundary value problem, you still work it the same way. But this is initial value. Solve y double prime equal to x, given that y of 0 equals 3 and y prime of 0 equals 1. So let's try this. If I have y double prime equal to x, my first way of solving this is to integrate both sides. So let's try that. What do I get when I integrate y double prime? Y single prime. What is the antiderivative of x? X squared over 2. Good. 1/2 x squared or x squared over 2. What else? Plus c. Okay? Now, I can get rid of that plus c. They gave me a fact that will help me get rid of it. They said that y prime of 0 is equal to 1. Y prime of 0 equals 1. So the 0 will be the x value. The 1 will be the y prime value. So let's see what we got here. 1 equals 0 squared over 2 plus c. So 1 is equal to c. We got it. So I'm going to plug that in right there. So I've got y prime equal to x squared over 2 plus 1. But I'm still not, the DE is still not solved because I don't have all the derivatives out. So let's integrate it in. What's the antiderivative of y prime? Right, good. Okay, what about the right side? X cubed over 6. Y'all see that? Add 1 and divide by your new power. 2 times 3 would be 6. Plus x plus c. How am I going to get rid of that c? Y of 0 equals 3. So 3 equals 0 plus 0 plus c. Y'all know that's going to be a 0 if you plug in 0. So 3 is equal to c. So my specific unique solution for this is I like that problem. That's called an initial value problem. And the only difference between an initial value problem and a boundary value problem is the x coordinates will change in your points. If it's an initial value problem like this one, notice your x's were both at 0. Okay? If it's a boundary value problem, that'll change. Solve this boundary value problem. Y double prime minus y equals 0. This is the equation. They gave us the solution. Said the solution is y equal to c1 e to the x plus c2 e to the minus x. They said this is the solution. But they want us to solve the boundary value. They want us to get the c's out. Get the c's out. So let's see what I can do here. They told us that y of 0 equals 0. and that y of 1 equals 1. Okay, let's see what we can do. 0 equals C1 e to the 0 plus C2 e to the 0. What is e to the 0? Okay, look at my statement there, and let's draw some conclusions right there. C1 plus C2 equals 0. What does that tell us about C1 and C2? What? C1 equals negative C2. They're going to be opposites of each other, aren't they? One's going to be positive, one's going to be negative. Or they're both going to be 0. Okay? So C1 and C2 are opposites. That make sense on that one? Okay, let's try this other side. Y of 1 equals 1. So let's see here. If y of 1 equals 1, 1 equals C1 e to the first plus C2 e to the negative first, right? Well, let's do this. I'm just going to leave them like that. I can't do anything. There's going to be decimal values. Let's plug in and just get it in terms of one of them. Let's do the C1 equals C1e plus, we know that, let's do it this way. Think of it this way. Can I think of it that way? Negative C1 equals C2. Let's do that. C2 would be negative C1 so if I factor out that C1, we could say C1 is equal to 1 divided by I'm just going to leave it in its exact form like that. It looks ugly. Otherwise, you'd have a decimal value. So what would C2 equal? Good job. The negative of that. They're opposite. So, get your writing hand ready here. Our general, it says solve the BVP, the boundary value problem. My solution would be y equals e to the x over e to the minus e to the negative 1 plus, well actually it should be minus because that's a negative one. You could probably write that. You've got a common denominator, and you could combine that even better if you wanted to. That's good enough. Leave it alone. We didn't even have to worry about trying to solve that differential equation or anything. They gave it to us. They gave us the solution. They said you just find out what the constant should be, C1 and C2. That it would make that work with the 0, 0 and the 1, 1. That's a boundary value problem. All right. I want to do a few of these. We're going to spend a good bit of time on. In fact, for lecture 3, I start off by reviewing this, okay? Reviewing this. Separation of variables is going to be your most easy method of, it's besides just straight integration, this is pretty much straight integration. Your easiest method of solving a differential equation. If the variables can be separated. In other words, when I say separated, on one side dy with nothing but y stuff. And on the other side of the equation, I want x's and dx. So all the y's on one side with a dy, and all the x stuff on the other side with a dx. That's what you're doing when you separate. If you get them all separated on each side, then you solve by just integrating those sides. Okay? So the algebra steps might be a little bit intense trying to get the variables all separated for yourself. Let's start off easy. We did this one tonight with Euler's method. We solved this one with Euler's method. Let's solve it analytically now because we can separate the variables. First, what's my first step to separate the variables? Who wants to help me out here? dx on both sides. Good job. Okay? Divide by y. Good job. Okay, so if I rewrite what I've got here, I'm going to have 1 over y dy 2x dx. Nice. Is everything good and separated now? Everything's separated, so, by the way, I love this problem. Integrate both sides. Love it. Stop, breathe, think about it. Look at both sides. Go back into your tool belt and say, what do I know how to do here? What is the antiderivative of 1 over y? It's natural log. 1 over x or 1 over y is natural log of y. It's actually the natural log of the absolute value of y, but let's just don't even worry about that, okay? Don't even worry. Ln y equals integral of 2x. 2x squared over 2, so you'll say x squared plus, you just want to do it on one side. When you're integrating both sides, put the plus c on one side, okay? Yay, I love this. Now, I'm not through. If I can get the y by itself, then I need to. If I can. Sometimes y'all going to have such a hideous answer, you'll be like, I'm leaving it alone because I'll mess it up if I keep on messing it up. Okay? That's my word of advice to you. If it's so nasty that you don't think you can algebraically get it solved for one variable, leave it alone. I'd rather give you, as much partial credit as I can without counting off a bunch because you do a bunch of dumb algebra moves that are not legal. Okay? So leave it alone if you have too many questions about it. You'll see plenty of examples that I work that I'm going to say, I'm not doing nothing else to that because it's nasty. Okay? How in the world can I get rid of the ln? What? Treat those two sides as if they're powers of e. So from now on, you're going to hear me say this is the e thing. Do the e thing. Okay? So we're going to do e, e. I don't know what you call that, but I call it doing the e thing. So e to the ln y just gives me y. Now here's what you got to think about. You have e to the x squared plus c power. In algebra, what was actually going on when you had to add powers together? What were you actually doing when you added exponents together? Multiplying two different expressions with the same base. Y'all remember that? Y'all remember that from basic algebra? Okay, now I'm going to ask you a question here. You're going to do this every time. E is a constant, right? 2.7, blah, blah, blah. e to the c part, what we're going to do is pull that out front as just a big multiplied constant. There's my solution. Questions on that? Anytime you do both sides with e like that, you're probably going to have that big constant issue happening. We'll see a lot more examples like that. That is a log law. Yeah, ln is actually log base e. Yeah. ln of e is 1. They'll cancel out. So e to the ln of y is just y. And we'll use that log law a bunch. Okay? dy over dx equals y squared plus 1, given y of 1 equal to 0. So let's do this the same way. First thing I'm going to do is multiply both sides by dx. Okay, what do I need to do to separate? Divide by the y squared. I would do that. Divide that whole quantity out of both sides. Oh, I love this one too. So I've got 1 over y squared plus 1 dy equal to dx. Okay, so get your integration bridges on here. How do you integrate 1 over y squared plus 1? If you pick u substitution, you'd be on the right track. You'd be like y squared plus 1 would be your u. What would your du be? 2y. Do you have a y in there to check off for your compensation? It is. This one's going to be inverse trig. U substitution wouldn't work. You don't have a y in the top. No, because you're not differentiating. Chain rule is just a derivative rule. So the integrated, he had it right. What did you say it was?
Inverse trig formulas.
What are the inverse trig formulas? Y'all look in your notes.
It's
This is 1 over x squared plus, or 1 over u squared plus a squared. The a squared will be 1. Inverse tangent. So this is actually going to be tangent inverse, whoops, of y. A is 1, so 1 over a would still be just 1. Tangent inverse of u over a, u would be y, so y over 1. There you go. Equals dx. What's the integral of dx? X plus c. Yay. Now this problem, don't forget this. This is something I want to warn you about. Make sure you check the problem and see if it's got an initial value. Check that over time. This one does. So let's work that right now. Y of 1 equals 0. 0 is the y. The x is 1. Use your calculator. Help me out here. What is tangent inverse of 0? So 0 equals 1 plus c. What's c equal to? Okay, so go back up there. Tangent inverse of y equals x minus 1. Let me see how smart y'all are. Can I get this one for y by itself? What do I need to do? Not multiply by tangent. I know what you're meaning. You're meaning the correct thing there. You're meaning it right. Take tangent of both sides. Take the tangent tree function of both sides. Tangent of tangent inverse will undo it. Does that make sense? Tangent of tangent inverse will undo it. So your solution would be y equals tangent of x minus 1. And notice you don't have any c's in there. Okay. Can we do one more and I'll stop? I'm going to stop anyway, right now. I'm not going to do that one now.